All right, we're going to get started on section 2.2 here and actually really get going into what limits are and how to work with them. So starting with limit of a function and limit laws. So from last section, we saw the limit occurs when finding the instantaneous rate of change of a function. Recall that this is the same as finding the slope of the tangent line to a point on the curve. So we saw this picture in the last section where we started off with 2 points that were further apart, and as we pushed this point Q closer to point P, the line connecting them became closer and closer to being the tangent line at that point. And it didn't matter in the second picture if Q was on the other side. As we pushed it closer to P, we got closer and closer to having the line between them being tangent. So if we take the limit that Q basically goes right up to becoming P or getting right next to P, then we end up with the line that is tangent to our curve at that point. Limits are used when we are interested in a function's behavior near a particular point C, but not at C. Okay, and I'll explain how is that useful here in just a second. So let's take a look here. How does the function x squared minus 1 over x minus 1 behave near x? Now, if you look at this, we have the x squared minus 1. We can say f of x equals x minus 1 times x plus 1 in the numerator. That's x squared minus 1, right? It's the difference of two squares over x minus 1, which means that these two things, you might be tempted to just cancel them out and say, hey, this equals x plus 1, all right? And you just say, all right, well, there, I'm done. Well, except that if you look down here at the graphs, this is the graph of x plus 1, what we turned it into. This is the graph right here of x squared minus 1 over x minus 1. So they are exactly the same except right here. Notice that right there, and notice this right here. One is an open circle, one is a closed circle, because at x equals 1, over here on the x squared minus 1 over x minus 1, we would end up dividing by 0. And so while it'll look like x plus 1 everywhere at all these points, at x equals 1, they are different. You end up with a hole in the graph right there. And so you can look here, right down here in this little table, you can see these values as, look what happens as we just get numbers that are close to 1. So we start with 0.9 and 1.9 and 0.99 and 1.01 and 0.999 and 1.001. So we're getting numbers closer, oops, still on the highlighter, closer and closer to 1, right? And notice what happens to these. These are the results over here. As our numbers, as we go down and get closer and closer to 1, we notice here we start with 1.9 and 2.1, and then 1.99 and 2.01, 1.999, 2.0001, 2.001, 1.9999999, and 2.00001. And if we just keep doing this, we're going to get closer and closer to a value of 2, which is what this one goes to. It goes to 2. It's 2 at x equals 1. However, this one, the one we were actually looking at, doesn't have a value there. So really all we can do is look and see what happens as we get close from both sides. As we approach from the positive direction and as we approach from the negative direction, what do our values start to go to? And the answer is they go to 2. They start moving to 2, okay? So its behavior near 1 is that it goes to 2. We can't look at its behavior at 1. We can't see what it does at 1 because it's undefined. We can only look at what it does near 1. Okay, so let's generalize this idea and we can come up with an informal definition of a limit. Okay, if f of x is arbitrarily close to the number L for all x sufficiently close to C, we say that f approaches the limit as x approaches C. And what we do is we write it this way. The limit, LIM, that wasn't a very good LIM. Let me try that again. LIM. The limit as x goes to C, this is how we would say that, or x approaches c, of some function of f of x is equal to some value L. All right, and this would be read, the limit of f of x as x approaches, sometimes people say goes to c, is L. So the limit as f of x approaches c is L. And from our previous page, we could look at that one and we could say the limit as x goes to 1 of x squared minus 1 over x minus 1. That limit, which we just found on the previous page, what happens to it? It starts becoming closer and closer to 2. So the limit as x squared minus 1 over x minus 1 as x approaches 1 is 2. All right, so let's take a look here. Observe the following three functions here. Here we've got x squared minus 1 over x minus 1. We've got a piecewise function here, x squared minus 1 over x minus 1 whenever x doesn't equal 1, and it equals 1 when x equals 1. And then we have just plain old x, x plus 1. So let's evaluate what happens at 1 for each of these functions. For the first one, x squared minus 1 over x minus 1 is f of x. F of 1 is undefined. We don't have an answer. For g of 1, f of 1 is 1, right? We'll get there. That's the value we'll get. If we go to either side of 1, we go back to the line that's there. But at 1, it's 1. And on this one, at 1, it's just 2, what it would be just for that line, okay? Here it was undefined because we have that hole right there, okay? So each of these functions, they're very similar to each other. They look very similar, but each of these functions has the same limit, right? They're all different at 1. They all look very similar, but they're all different at 1. But they have a limit of 2 as x approaches 1 or goes to 1, okay? Note that the limit value does not depend on how the function is defined at the point being approached. We're just looking at nearby it. And for all three of these functions, right next to 1 to just either side, to just this side or this side or this side or this side, it's all really close to being 2. It's all going to 2. So we can look at this for graphs. We can start taking limits. So let's look and see what the following limits are by doing the same sort of thing, by looking at what they're approaching as we go here. So the limit of g of x as x goes to 1. Okay, well, if we look at this one, if we're looking from the positive side, we're going down toward 0. So from that side, all the values start going to 0. From this side, they're all going to 1. Which means it's not doing the same thing on both sides, which would mean we would say this is undefined. All right, let's look at g of x as x goes to 2. Okay, here we're looking at this. Maybe I'll do it in a different color here. This one is from the negative side, it's going to a value of 1. From the positive side, it's going to a value of 1, which means so for on both sides, it's going to a value of 1, therefore the answer is 1. All right, if we look at g of x here as x goes to 3 here, now the value at 3 is 1, but as we approach 3 from the negative side, from the left, it's going to 0. And as we approach it from the right, from the positive side, it's also going to 0. So the limit here is going to be 0. And then the limit of g of x as x goes to 2.5. Well, here's 2.5. Let me get a different color here. Here's 2.5. So we're going toward this point right there. As we approach from the positive side, from the right, from the positive side, we're getting a value of 0.5. And as we approach from the negative side, from the left, we're going to a value of 0.5. Okay? So this is 0.5. There you go. And those are the limits for those things. Let's take a look at a couple of special functions. Define the identity and constant functions, and then specify the limits. So the identity function here is just y equals x, or f of x equals x. That's our function right there. And so what's the limit? Let's take a limit. Take a limit as x approaches x naught, whatever x naught is, of f of x. And this is simply going to be the limit as x approaches x naught of x, which is just x naught, whatever it is. Because in this function, whatever you plug in is what you get. So if we go to a point like here, or even if we said, all right, let's look at 1. When we plug 1 in, we get 1. And so as we approach from either side, we're going to 1. And the same thing would happen if we did 2. We'd approach from the left, and we'd approach from the right, the negative and the positive side, and we'd get 2. So whatever we're approaching from is what we get. So what we're saying here is the limit of the identity function is always just whatever the result of the identity function is there. So we've got that. Now let's take a look here at a constant function, where we've got f of x equals k. So here, the limit as x approaches any value of x, any x naught, could be 7, could be 55, could be 100, any value of f of x is just the limit as x approaches x naught of some of k, whatever our constant value is, because it could be 3, like f of x equals 4, or f of x equals 3, or f of x equals 77. It's just going to ultimately equal k. So no matter what value we look at, no matter where we're approaching, we're always going to get that same constant value. So basically, the limit of a constant is the constant. Okay? Make sure you remember that. Don't mess that up. That's one of the easy ones. Really easy ones. Can almost guarantee you'll see something like that. So make sure you pay attention. The limit of a constant is a constant. So for example, like the limit as x goes to 6 of the function, y equals 8 is 8. That's it. Up here, example, limit as x goes to 2 of x is just 2. Okay? So example, an example. Okay? So pay close attention to those and make sure you don't mess up that constant one especially. All right, limitless. There are times when we don't have a limit. We talked about one a couple pages back where we had an undefined result. And here we've got some functions where we're not going to have a limit at certain places, and explain why they have no limit as they go to 0. Well, as we go to 0 from the left, from the negative side, we're getting 0. As we go to 0 from the right, from the positive side, we're getting 1. And so we have 2 different results there, which means we're not going to get a value for it. The next one, you'll notice as we go towards 0 from the negative side, we're going down to negative infinity, right? As we go from the positive side, we're going up to positive infinity. So again, they don't match. It's broken. It's disconnected. We don't have a limit there. And so both of those are not going to give a limit. Now, take a look at this last one. If you notice, it's just basically, if we were like to zoom in on this, it's just going like this, like crazier and crazier back and forth. Which means, as we try to approach, we're basically going to be jumping back and forth between 1 and negative 1. We're going to get all these crazy values in between as we're approaching from this right-hand side, which means if we come from the left, it's nice and smooth and easy. We go towards 0. But as we come from the right, we're going towards every value between 1 and negative 1. We have nothing that it's going to. So this one is also going to not have a limit. So there's a few situations there where you may not have a limit, where it doesn't exist, when you have a break in it where it doesn't exist, or also where it's jumping all over the place or stuff like that. Okay, here are some limit laws. You need to make sure that you go through and have these down. But basically, it's saying the sum rule is that we're saying the sum of two different limits. So we're saying the limit of f of x as x goes to c is L, and the limit of g of x as x goes to c is m. And so if we take the limit of the sum of those two functions, it's just the sum of their limits. That's the first one. The difference rule, it's the same. It's the difference of the functions. It's going to be the difference of the limit. If you have a constant multiplier, you can almost think of this as like telling you, like say if k was 3, it's telling you add a function to itself 3 times, which is basically just back to being rule 1. So the limit of a constant times a function is just the constant times that limit, because you're basically adding that function to itself, or that limit to itself, k number of times. Product rule is basically the limit of the product of the functions is just the product of the limits. So hopefully these are all pretty intuitive. The quotient rule, again, the quotient of the limit of the quotient of the functions is just the quotient of the limits. The limit of a function to a power is just the limit to a power, as long as n is a positive integer. So that's a good one. And then the root rule, well, that's the same as the exponent rule, as long as n is a positive integer as well. It's just, remember, it's just this. It's just 1 over it. So 1, 4, and 6 are the main ones. Just make sure you have those down, and then the other ones are kind of just, variations of those ones. If n is even, we assume that the limit of f of x as x goes to c is L is greater than 0. So be careful of that when we're talking about that rule there. All right. So these laws, along with our discussion about the identity function, allows us to plug in the values we are approaching. Usually. There will be times when we can't do that, but we'll work on them later. But usually we can just plug in a value. Even if there's going to be a hole there, we can get rid of the hole by dividing it out and then plug in the value and see where it was going and what it was doing. So usually we can just do that. So let's take a look here. Find the limits. The limit of x cubed plus 4x squared minus 3 as x goes to c. This is limit as x goes to c of x cubed plus 4x, plus the limit as x goes to c of 4x squared minus the limit as x goes to c of 3. So now we can just use our rules. We can actually here just plug this in. This first one is c cubed. We plug in c for x. The second one is 4c squared, and then the last one is just the limit of a constant is just the constant. So there you go. All right, and that's our answer for that one. So for the next one, okay, we basically just have to go ahead and do it, and we look at this. We can just plug in 1. We don't have to go through and write the whole thing out. I mean, we could write limit of x to the 4th plus the limit of x squared minus the limit of 1 divided by the limit of x squared plus the limit of 5. We can do all that, or we can just plug this in, because we're not going to have any issues plugging this one in. As long as we don't end up with a hole or a does not exist or something like that, then we can just plug it in. And so we have 1 to the 4th, which is just 1. 1 squared is 1 minus 1, so that's 2 minus 1. That's a 1 in the numerator. And then in the denominator, we have, oops, that was supposed to be a plus. We have 1 squared plus 5, that's just 6, so it's just 1/6. And I might go ahead and write one more little example in here for you. Let's take a look at the limit as x goes to pi of the cosine of x plus 3. Again, we can just plug in the pi, because cosine of pi doesn't give us any issues. We can actually do that, so we can just do cosine of pi plus 3. The limit of 3 is 3. And the cosine of pi is -1 plus 3 is just a 2. So as long as we aren't given any really kind of issues, we can just start plugging them in. So let's take a look at one more. Actually, I'll leave this one for you to do, and I'll put the answer in the notes for you to look at, okay? All right, so I think I'm going to stop this video there, and I'll pick it up in the next one for another part. All right, thanks.